Now let us look at the next problem. Let there be a spherically symmetric charge distribution with charge density varying as rho equal to rho naught 5 by 4 minus r by r up to r equal to r. Okay, where r is the distance from the origin. The electric field at a distance r, where r is less than capital R, from the origin is given by. Now in this problem we have to apply the concept of Gauss theorem or Gauss law. So what Gauss has to say is that the flux that emerges out of charge distribution from a Gaussian surface is given by Q enclosed upon epsilon naught. Now in this given case, let us say we assume a Gaussian surface which is spherical in shape, okay, and the electric field at this point, since this is a symmetric charge distribution, the electric field at each and every point on the sphere will be radially out. Okay, so if we find out phi, that is equal to E dot ds. Now let us say the electric field strength is E and the magnitude of which is capital E, then E and ds, the small area that you consider over here on the surface, they will be always parallel to each other, okay, because the ds vector is normal to the surface. So the angle between the two is 0, so it can be written as E ds, E being constant because it's a symmetric case. And for a sphere, the value of ds integral will be 4 pi r square. Okay, now this is one. Now second is, we have to find out what is the charge enclosed. For that we have to consider small elements in the form of thin spherical shells of radius r and thickness dr. Okay, let us say we take x and dx. So what is the volume? Volume will be given by dV equal to 4 pi x square, that is the surface area, into the thickness dx, so it is 4 pi x square dx. What is the charge dq in this spherical shell? In this shell, let us say the charge is dq, that will be given by density, charge density at this point into its volume, which is rho naught 5 by 4 minus x by capital R. This is rho, and dV is given by 4 pi x square dx. So now you have dq. If you integrate this expression dq, you will get charge, total charge that is enclosed, and in the right hand side you have to put the limits of x, which is from 0 to small r, okay, where r is this Gaussian surface radius. So rho naught 5 by 4 minus x by r 4 pi x square dx. So if you integrate this, you will get rho naught is common, it will come out of it. 4 pi is also common. Now we have integral of 5 by 4 x square dx minus of integral of x cube by r dx with limits 0 to small r, 0 to small r. Okay, now this can be further written into as 4 pi rho naught 5 by 4 x square will become 5 by 4 x cube by 3, 5 by 4 x cube by 3, and the limits are 0 to r, minus this will become x to the power 4 by 4r with limits 0 to r. Okay, now if you substitute the values of upper and lower limits, you will get 5 by 4 r cube by 3 minus r to the power 4 divided by 4r. Okay, now this is charge enclosed, and we know that electric field, that is the flux, into 4 pi r square, that is the total flux, is given by charge enclosed upon epsilon naught. Okay, now if you substitute the values, E into 4 pi r square equal to Q enclosed, that is 1 upon epsilon naught, and we have 4 pi rho naught, and this r cube and this r to the power 4, we can take r cube as common, then we will get, and 4 also can be taken out, this 4 and this 4 can also be taken out, so we will get 5 by 3 minus r by capital R. Okay, now this four pi cancels out, r square, then here it is cube, so this 3 will go, and you will get finally E as equal to rho naught upon 4 epsilon naught r 5 by 3 minus r by capital R. Okay, so among the 4 options, option B is correct.